right, welcome back to the final session of the day. It's a session about cube attacks, which will have two talks in it. The first one is about a new practical cube attack via recovering numerous superpolys. It's going to, so it's authored by Minjiang and Yao Sun, and Min will give the talk.
Good afternoon, everyone. I'm Zhang Min. I'm very pleased to give a presentation here. My topic is a new practical cube attack via recovering numerous superpolys. In this presentation, firstly, I introduce some background and our main contributions. Secondly, I talk about improved graph-based model. And thirdly, I show our practical key recovery attack. Let's start with the first part. Cube attack is one of the most powerful tools of attacking stream ciphers. And we can sum up the Boolean polynomials over the cube Ci to obtain the polynomial P, which is called the superpoly of the cube. With this polynomial, we can do a cube attack. P should be balanced, and in the offline phase, we generate the polynomial P, and in the online phase, we need to query the oracle many times to get the value of P. Then we can obtain the equations. After obtaining the equation, we could filter out half of illegal case, and the complexity is this. More superpolys may be lower down these complexities. There are two important steps in cube attacks: recovering superpolys correctly and solving the systems of superpolys efficiently. In many years' work, the problems of recovering superpolys correctly have been solved complete in 2020. So we focused on solving the systems of superpolys efficiently. Many researchers tended to solve the systems of linear or of superpolys with balanced bits. But systems are easy to solve and hard to construct. So we turn to search for and solve the nonlinear superpolys. Technically, it is very hard, unless the systems have particular features. We observe that systems of superpolys could be sparse, asymmetric, and highly overdetermined. If we take advantage of these features, maybe we could solve the nonlinear systems. There are two key steps for attacking triviums. First, obtain numerous nonlinear superpolys. Solving the systems of nonlinear superpolys practically. We summarize our main contributions as three parts. First, improve the graph-based model. Second, propose a new testing approach. And thirdly, we apply our method to practical key recovery attack. Here is the results. We improve previous highest round of trivium that can be attacked practically. And these are our main contribution. Let's begin the first contribution, improved graph-based model. The novel graph-based model was presented by DDGPs in 2022. It could speed up the recovery of superpolys. In the model, the vertex stands for a variables in an ENF, and age implies the presence of monomials in an ENF. Different from the traditional age, from a vertex to another one, DDGP's age point to the site of vertices. It indicates the monomial BC is present in the ENF of A. Here's a toy example. These are ANF of Z, Y1, and Y2. The vertex Z have two outgoing edges, which pointing to the Y1 and Y1, Y2. This means that the two monomials appear in the ANF of Z, and the Y1, Y2 also have several edges pointing to the axis. We have seen that the set of vertices and edges represent an algebraic structure. To determine a monomial appears in an ANF, we need the concept of valid graph. A valid graph implies a specific monomial appears in an ANF. In this case, we require only one outgoing edge of vertex can be activated. If E1 is activated, this means Y1 and Y2 appear in the ANF of Z. So a valid graph need only one outgoing edge for every vertex. This is the one-level transition. If we consider two-level transition, x1, x2, x4 appears in the ANF of Z with respect to axis. A valid graph, also called a trail by DDJPs, they draw like a tree, and they use a doubling edge to represent the Z pointing to Y1, Y2. The definition of valid graph is as follows. No isolate vertices, and for any non-bottom vertex, they have only one outgoing edge. The transitional trivium could be represented as algebraic representations, so they construct the graph-based model. A valid graph means a monomial appears in the superpoly. DDJPs also propose three consecutive bit two patterns. A two pattern with two subgraphs have the same top vertices and bottom vertices. So we could rejecting pairing trails to speed up the recovering superpolies. In this work, we studied three problems. Which kinds of trails can be rejected by a two pattern? And how do two or several two patterns work correctly when used simultaneously? Given a two pattern, we say alpha 0, alpha 1. We consider a trail tau, which contains alpha 0. There's a pairing trail tau and tau minus alpha 0 plus alpha 1, deduced from the pattern. Pairing trails make no contributions to the Boolean ANF. So if they appear together, we could discuss them. Intuitively, a two pattern seems could do this directly. But it is not the fact. Tau minus alpha 0 plus alpha 1 may not be valid. Let's look at the example. The left one is tau and the right one is tau minus alpha 0 plus alpha 1. After replacing the alpha 0 by alpha 1, we found that the vertex C118 have two outgoing edges. It is not valid, and it may be leading to an error. So, on seeing that, we propose sufficient conditions on tau minus alpha 0 plus alpha 1 be valid. And there is the propositions if the condition is satisfied, then both tau and tau minus alpha 0 plus alpha 1 could work correctly. So this answering the first problem. And the second problem, how do two patterns work correctly when used together? The series also contain sufficient conditions so that alpha and beta can work correctly when used simultaneously. And the mathematical details could be found in the paper. For the third problem, the theorems answer the question by give sufficient conditions on how do several two patterns work correctly. After answer 3 questions, we propose a graph-based algorithm using more two patterns to reject pairing solutions. There are 6 cubes used in our attack. The first algorithm is DDJP's graph-based model with 3 consecutive bit patterns, and the parallel and the second one is a parallel version of the first one implemented by us, and the third one is our improved graph-based algorithm with dynamically found new pattern. It can be found that our model is much efficient. This is because we think it is because we have much fewer the number of trails, and we think this is because we do much fewer useless complications, and this is our main results. Let's look the next contribution, practical key recovery attack. In the offline phase, we recovered 13,000 nonlinear superpolys, and the mother cube is this. Its size is 1449. And in the online phase, we need to solve this nonlinear system practically. The system of superpolys have some characteristics. First, there are 1,300 equations with 80 unknowns. So this system is highly overdetermined. The other 2 characteristics is sparse and asymmetric. Why do we say our system are sparse? Because the totally degrees are high, and the largest superpolys have 278,000 monomials. According to our experiments, we can see that most superpolys have less than 1,000 monomials. Traditionally, sparse system is slightly easy to solve. The appearing times of variables is asymmetric. We also construct 16,000 experiments in the picture. We can see K9 appear 23 times and K58 appears more than 1,300 times. This tells us assign the wrong value to K58 easily leads to a contradiction. You may be asked why we not solve the system directly by site solver or global basis method. There are 2 drawbacks. First, some case cannot be solved. Second, the complexity is hard to estimate. So we propose a test method. We are testing the values of variables to check for a contradiction. If we guessing xk equal to 1 leads to a contradiction, xk must be 0. Below is the algorithms of testing variables. First, we sort the variables by appearing times. Secondly, we test whether the variables equal to one or 0 to lead a contradiction. The text method is set solver and group the basis method. And after testing 80 variables, if there are some variables also could not be determined, we enumerate its values. So because our tests are fast, we cost 8 to 9 hours on average. The complexity is determined by the number of undetermined variables. We also display the number of undetermined variables in our experiments. We found there are no bigger than 37 for 16,000 different cases. About 90% case can be recovered completely without extra enumerations. The complexity consists of the size of the mother cube is 49, and the largest number of undetermined variables is 37. So the overall complexity is this. It can be done practically. This is the summary of our work to finish the presentation. Improve the graph-based model and new testing algorithm, a practical key recovery attack. And our method also apply to higher rounds. Thank you for your attention. Any question?
Thanks a lot. Do we have questions from the audience?
Thanks a lot for the nice talk and nice work. I just have a question on how do you test the actual value for the keys in the solving system? I mean, how do you decide if a value of if these 37 key values are right or wrong? I probably missed something.
Oh, for example, if xk equal to 1, it is a wrong value. Then in the set solver, it will quickly return it is no solution. So we know xk equal to 1 is wrong. Then the xk must be 0. I don't know if the meaning is this or.
Yeah, thank you very much.
Okay, thank you.
Any other questions? If not, then let's thank Min again.